This is AP Chemistry topic 9.9, cell potential under non-standard conditions. Today's objective, explain the relationship between deviations from standard cell conditions and changes in the cell potential. So far we looked at E0 and what it means in only standard conditions, such as 1.0 molar, 1 atmosphere, and 298 Kelvin. In the real world, that's not necessarily the case. So the cell potential will differ from our predictions because it's not normally like the standard conditions anyway. So it will vary as you change the concentration of the solutions in the system, whatever the case may be. So electrochemical cells are not at equilibrium, they are moving towards equilibrium. Since they are not at equilibrium, we cannot use Le Chatelier's principle to predict because these are not at equilibrium just yet. So we know that the standard cell potential is 1 molar in 1 atmosphere. The value for Q, the reaction quotient, would have to be 1. As a cell reaches equilibrium where Q equals K, the magnitude of the cell potential will decrease to 0. A value of 0 for the cell potential means that the reaction has reached equilibrium. So we've kind of used this already, the Nernst equation. It shows a relationship between the cell potentials at non-standard states and standard states. E equals E0 minus RT over N times F, natural log of Q. You should be able to explain qualitatively how non-standard reactions will affect the voltage of a cell. You should understand how changing Q will change the voltage. When the conditions deviate from the standard conditions, meaning Q is less than 1, in a direction that will take the reaction further away from equilibrium, the magnitude of the cell potential for the non-standard cell will be greater than the standard potential. So let's look at this cell, and it has the reduction reaction of zinc 2 plus 2 electrons produces zinc as an E0 of negative 0.76 volts, and it's an oxidation reaction of calcium producing 2 electrons and Ca2 plus, E0 of positive 2.87 volts. And let's say that you do it, you get the overall reaction of this zinc 2 plus calcium produces zinc plus Ca2 plus, E0 equals 2 plus 2.11 volts. So how do you get the value of K? So you have to figure out the G sub 0 first. So let's use this equation here. Negative 2 moles, because that's the amount of moles that are of electrons that are kind of shared, I guess you can say, or they're used up in this reaction, times Faraday's constant, times the volts for the E0, the 2.11. And remember that 1 joule over 1 volt times Coulomb, that's your constant. That equals negative 407,000 joules. To find the K, it is the E of the opposite of the delta G G0 of the, so that's plus 407,000 joules divided by your R, the 8.314 joules per mole Kelvin times your Kelvin. That will be 2.2 times 10 to the 71st. That is going to equal your K expression, 2.2 times 10 to the 71. And that equals Ca2 plus over Zn2 plus, and that's your products over reactants. So assuming we're at a standard condition of 1.0 molar, your Q will equal 1. If we change the concentration of the zinc ions to 2.0 molar, your K value would decrease to 0.5. This means that the new Q value is further away from the K equilibrium than 1. So they can also apply the Nernst equation. So the E0, this is your volts from the overall reaction, minus all of this, again, times the natural log of 1 over 2. The 1.00 molar is still the standard for the calcium, but we changed the zinc to 2.00 molar. Notice how much and how little the voltage changes, 2.12 volts. A concentration cell is another type of electrochemical cell. It is similar to the cells that we saw last few lessons, but you have the same half reaction in both beakers, each with a different concentration. We can predict the direction that the electrons will flow by looking at which direction, is the thermodynamically favorable one to go reach equilibrium, so that you have both equal concentrations on both sides. So in this example, the overall reaction would be copper solid plus Cu2 plus, and that has a concentration of 1.0 molar, producing copper solid, Cu2 plus, but the concentration is now 0.10 molar. So because it's the same thing, the voltage, the E0 is 0. And then you would plug in the rest. So you have your RT, so 8.314 times 298 divided by, so looks like we have 2 moles that are being transferred, times Faraday's constant, and all that times your natural log. So our product was a copper 2 plus at 0.10 molar, and that's going to be over the reactant's 1.00 molar. When you do the math, you end up with 0.030 volts. So why does it equal 0? Just really quick. So in a concentration cell, the E0 is 0 because the reactants at the anode and the cathode are the same. So we're going to do an example of this in a bit, so shouldn't be too bad. So here's a brief summary of the delta G0, K, and E0 cell relationships. You might want to look at these and understand how you can get one to solve the other, etc. So consider a thermodynamically spontaneous cell at 298 Kelvin. It's composed of 100 mLs of 1.0 molar Fe2 plus in one beaker and an iron electrode, and 100 mLs of 1.0 molar manganese 2 plus in another beaker with a manganese electrode. The beakers are connected. They're able to the electrons are able to flow. You have a voltmeter, and you have your reaction. Fe2 plus produces manganese solid plus Mn2 plus, and then iron solid. Your E0 is plus 0.74 volts. Qualitative to describe what happens to Q. So you have our first scenario. You have 0.10 moles of iron 2 plus, iron 2 nitrate, and it's added to the iron 2 plus beaker. So what's going to happen qualitatively? Adding the moles of iron 2 plus will increase the concentration of iron 2 plus in the reduction cell, and this will cause the value for Q to decrease, and your conditions will take you further away from equilibrium, so that Q equals 1. Q is less than 1 now, and thus the voltage would increase. Adding distilled water to the iron 2 beaker. Adding distilled water will decrease the concentration of iron 2 Fe2 plus, and this will cause the value for Q to increase and this condition will bring you closer to equilibrium, and then thus your voltage would decrease. You have 100 mLs of distilled water and you add it to both beakers. What's going to happen? Adding the distilled water will decrease the concentration of both by the same amount. This will not cause the value of Q to change, and therefore the voltage will remain the same. So look at these different scenarios. They may ask you, like, what can potentially happen if you change this or add this, etc. So you have a zinc concentration cell below at 208 Kelvin. The Zn2 plus in the beaker, so the left one, it is 1.0 molar. So this is 1.0 molar, and there's zinc 2 plus in this solution. There is your half reaction with your E0 of negative 0.76 volts. Calculate the potential if the right beaker is filled with 2.0 molar. So this is going to be 2.0 molar zinc 2 plus. So before we can figure that out, we have to know who is considered the reactant and the product in this particular concentration cell. Sounds weird saying out loud, not gonna lie. Okay. So just a couple of things to know. The reaction will go until your concentrations are equal to each other. So thinking about this, what needs to happen for this to kind of reach an equilibrium? So here, if I have the zinc solid, both my electrodes are zinc, so it will dissolve into solution. Over here, the zinc 2 plus will plate, meaning it's going to add to the electrode to ensure that there's less in the solution and more onto the actual electrode. So this means that zinc on the left side will go into solution. The zinc on the right side, the zinc 2 plus, will actually become solid, meaning it's going to add to the electrode. So what is being reduced or oxidized? So your oxidation numbers are going from 0, on this first one, the 1.0 molar, it's going from 0 to 2 plus. That means electrons are lost, so this is oxidation. And if oxidation is occurring somewhere, this is your anode. So that means the other side, your 2 plus becomes 0, so technically you're gaining electrons, so this is reduction. So that means that the right side is my cathode. And this is where reduction is occurring. So I'm going to kind of color code this a little bit. So then this one will be the reduction, will be the green one. I'm going to rewrite this somewhere, don't know where. And I'll make the oxidation blue. Ooh, it's ugly. I'll make it a different blue. Okay, so to figure out who is going to be the reactants and products, you have your zinc plus zinc 2 plus, and this is your 2.0 molar. You are going to produce zinc 2 plus, that is 1.0 molar, plus your zinc solid, and that's the green one over here. And then I'll make that one solid. So now you see that your 1.0 molar is the product and your 2.0 is the reactant when you're setting up your Q expression. So let's finish this up. E equals E0 minus RT over NF times the natural log of the products times over the reactant. So let's see if I can fit this. So because these are the same thing, the same cathode and anode, your E0 is going to be 0. So that helps a lot. 0 volts minus, I don't have much space, so 8.314 times 298 over 2 moles of electrons times 96,485 times natural log of 1.0 over 2.0. I do my work. I'm going to just put this over here. Sorry, it's a mess. It's going to be, I do my work on my calculator, I end up with 0.0089 volts for my final answer. Last question. Identify the cathode and anode and draw an arrow to represent the flow of electrons. Well, we kind of did that already. So my cathode, it is the 2.0 molar side, and my anode was the 1.0 molar side. Remember that electrons flow from anode to cathode, so now you need to indicate that. So let's just use an arrow, and we'll just say that electrons are going from the anode to the cathode. All right, if you have any questions, please let me know. Thanks.